Good morning. Hello, everyone. Thank you for joining us. This is our new webinar, In Situ and 4D STEM Analysis using the Gatan ClearView camera. My name is Fernando Castro. I'm an application scientist for Gatan. I'll be your host today, and I'm very excited to welcome a great group of speakers to present some of their exciting research they've been doing using the ClearView camera. Today we have three speakers, Dr. Arashdeep Singh, Mr. Daniel Zangane, and Professor Robert Klee, all from the University of Illinois, Chicago. So Arashdeep is a postdoc in Professor Robert Klee's nanoscale physics group. He uses electron microscopy and materials modeling to develop fundamental atomic scale structure property relationships in functional materials. Daniel is a third-year physics graduate student in the nanoscale physics group at UIC. And his PhD research focuses on the atomic scale and in situ characterization of nanoscale systems for energy storage and optoelectronic applications. And last but not least is Robert. He's a professor and the head of the UIC physics department. He serves as the director of the nanoscale physics group, the academic director of the electron microscopy core facilities at the Research Resources Center at UIC, and is the co-director of the UIC Institute for Functional and Regenerative Materials. As a scientist, he focuses on atomic resolution characterization of functional and regenerative materials using state-of-the-art transmission electron microscopy. So some quick housekeeping notes for the webinar. If you have any questions, please submit them through the questions pane in the GoToWebinar interface. If you have any issues with connectivity or anything like that, you can also submit those questions through the interface. Someone will reach out to you to assist you with that. And any questions that come up through the presentation, also please submit them through the same interface. We'll answer the questions at the end of the webinar presentation. So that's all I had to get started. I'll hand it over to our first speaker, Professor Robert Klee.
Good morning, everybody, and thank you, Fernando, for the great introduction. Thank you all for tuning in. As you heard, what we'll be talking about today is our in situ and 4D STEM analysis using the new Gatan ClearView camera. And the intent of this webinar is to report on our experience with the ClearView camera in this nanoscale physics group here at UIC. We have been testing the camera for the last couple of months, and we're trying to give you an overview of the results that we have achieved with this camera, ranging from 4D STEM analysis of thin film materials to in situ videography of phase transformations of battery cathodes, as well as the dissolution and corrosion of particles in graphene liquid cells. Now, let me get started. The folks that you saw in the beginning when Fernando introduced all of us are giving the presentations, but here are the people who are also in part responsible for this work. And this is an older photo, but I just wanted to highlight some of the contributions, especially from Yingji, who used to be a postdoc in my group, and she did a lot of the work on the in situ work. And you've seen Fernando and Arashdeep already. And I also have to acknowledge our funding sources. The research you'll see is supported by the National Science Foundation through those two grants, as well as these two Department of Energy grants and these two grants from the Department of Defense. All right, so let's get started with the science part. The results that you see were acquired using the JEOL ARM200CF at UIC. This is a cold field emission aberration corrected microscope equipped with a number of, this was how before we tested the ClearView camera, it was equipped with a series of annular dark field and bright field detectors. We have a series of stages as well, and the Gatan Continuum GIF. And again, this microscope was purchased using these two NSF grants over the last couple of years. Now, here are some details on the ClearView camera that we have been testing for a while now. This is a scintillator camera or a CMOS camera that can be used to take very high signal-to-noise ratio images, as well as videos at a 4K resolution and 50 frames per second for faster in situ and bin acquisitions. You can get up to 1600 frames per second. We'll show you later what you can do for 4D STEM analysis to improve the the frame rate even further, and it can be integrated with digital micrograph to really do pretty seamless analysis. And I hope at the end of this webinar you have an idea of the range of different applications that can be used using this camera. All right, so what we mainly going to be focusing on in my group is scanning transmission and electron microscopy. Traditionally, you probably have seen this slide many times. We scan the probe specimen. We use this annular detector to integrate and really just take a atomic resolution high angle annular dark field image or a Z contrast image, and then we can combine this with EELS spectroscopy when we use the electrons that scatter to lower angles and couple into the spectrometer to then perform measurements of the local density of states. So we can combine this with the imaging mode and then take spectrum images. Now, with this new camera, we actually don't have the scintillator integrated detector anymore, but we have a pixelated detector. And this now allows us to really take a probe by probe convergent beam diffraction pattern, and then we can apply numerous virtual detectors to, for example, again, give us something that looks like a high angle annular dark field image, but we can also use the other information contained in the diffraction patterns to obtain, for example, differential phase contrast or 4D STEM images. Now, I mentioned that we're going to do EELS, and you'll see a number of EELS spectra throughout this presentation. Just very briefly, EELS spectra, of course, measure transitions from occupied into unoccupied states above the Fermi level promoted by the incoming electron beam. We're going to look at transition metal edges. And these can be used for, as shown here in the case of manganese, these can be used, for example, to assess the valence state, or we can look at the titanium edge, for example, here. The changes in the fine structure also allow us to assess the local valence state. And so that will be important for some of the presentations. And this is just a very quick brush-up reminder. Now, over the last couple of years, we've seen this huge revolution in resolution. The aberration correction has really allowed us to push beyond the diffraction limit of conventional electron-optical lens systems, and we are now pushing towards like the 50 picometer spatial resolution using various approaches, including 4D STEM and tachography. Now, this is sort of like a conventional image that you can take on a day-to-day basis of like sub-angstrom resolution. And what I want to point out here is atomic resolution image usually requires 10 to the 5 electrons per angstrom square per second. Some of the work you'll see later on, we really take advantage of the low dose capabilities of the ClearView camera. You'll see that we push this dose down by 5 orders of magnitudes to get into the 20 to 50 or so electron per angstrom square per second regime, while still obtaining atomic resolution images. We also have seen huge improvements in the electron sources using monochromated monochromators, and this allows us now to do monochromated EELS, such as vibrational spectroscopy. We won't be talking much about this today here, but we've seen a similar revolution in resolution for in-situ microscopy, allowing us really to now go and minimize the window thickness thanks to these MEMS-based silicon nitride devices, or if you go further and use graphene liquid cells, we can really achieve atomic resolution images of samples in a liquid environment. And so the need or the desire really for in-situ experiments really or the ClearView camera really shows its advantages when trying to do in-situ microscopy. And you'll see a couple of examples here. We use, for example, a holder like this for observing in-situ electrochemistry, and where we're going to need very low doses and want to observe dynamic behaviors. Or we can use these graphene liquid cells that I mentioned earlier that was introduced by the Oliver Satos group in 2012, showing there that you can really do atomic resolution imaging in a liquid environment of the growth of particles. And we'll show you later on the inverse behavior here, where we see the dissolution and corrosion of particles. And here is some work from our own group that we could show that you can really do atomic resolution imaging of ferritin proteins in the scanning transmission electron microscope mode using these graphene liquid cells. And you can really start to see here individual atoms of iron in the graphene liquid cell. All right, so with that primer, I want to hand off the presentation to Arashdeep Thint, who's going to tell us about 40 STEM of oxide thin films, and Arashdeep's going to get next.
Thank you, Professor Klee. Hello, everyone. Today I'll be talking about structural transformations in thin films using 4D STEM. So I'll be covering solid state reduction of square planar nickelates on strontium titanate substrate, and also how strain affects the growth of strontium hafnate films on scandinates. First, just a brief introduction. So in 4D STEM, we have a scanning probe that rasters through the sample plane, and using various annular detector, as mentioned earlier, we can collect images corresponding to real space, as well as when we have a pixelated detector like ClearView, we can also collect simultaneously the images of the 2D projection of the transmitted probe, as shown on the right. So basically, predominantly we can run 4D STEM in roughly two modes. So one is a high convergence angle, where we get very high spatial resolution in real space, as shown in the atomic resolution image of cadmium telluride here, and correspondingly we get a convergent beam diffraction pattern. So using this kind of technique, we can do differential phase contrast. We can look at the electrostatic fields around atoms, around defects. We can also create virtual detectors where we can enhance or suppress the contrast of various different sublattices depending on their Z number. Another technique is the nano beam diffraction mode, where we use a low convergence angle that gives us a lower spatial resolution in real space as compared to the previous mode, but we get a high resolution in the reciprocal space, so as shown below here. So using this kind of mode, we can look at strain, we can look at crystal orientations, we can also look at polarization. So I will be predominantly focusing on the nano beam diffraction mode to look at the structural changes that occur in these thin films when we are growing them under different conditions. So this is just an example of a typical kind of data that we can get from using the ClearView camera. So on the left, the green marker shows the position of the beam as it's rastering through the sample plane, and then we have on the right an unprocessed diffraction pattern. So we can clearly see that even at such high frame rates, we can get very good signal to noise ratio, and it enables us to accurately map strain without worrying about sample drift. So first I'll be talking about the solid state reduction of nickelate thin films. So just an introduction. So the superconductivity is achieved by reducing the perovskite phase to an infinite layer phase in these square planar nickelates. So on the left, we have a strontium titanate substrate with a perovskite structure, and on top of it, we have a nickelate, so typically neodymium or strontium nickel oxide perovskite. So we have the nickel cation is coordinated by 6 oxygen atoms. So what we do is we use a topotactic hydride-based reduction to drive out oxygen from the perovskite phase, such that we lose the apical oxygens here, and what we achieve is a square planar nickelate, and it's an infinite layer phase as going along this direction. So this phase is shows superconductivity. That's why it's very interesting to control the synthesis and obtain high quality square planar nickelate films. However, there are some issues with this process. First of all, the process is very, very harsh, and it often results in phase separation into binary oxides or pure metal phases, which is undesirable. And also another issue is that the oxygen removal is not very selective. It can also remove some of the square planar oxygen atoms, which is not necessarily what we're looking for. So Professor Charles Ahn's lab at Yale University, they developed a new method where we use a strontium titanate substrate. We grow neodymium nickel oxide perovskite phase, and we coat it with aluminum under high vacuum. So the idea here is that aluminum's high affinity with oxygen forces the perovskite phase to reduce into the oxide phase, reduce into the square planar nickelate phase. So this is the chemical reaction. So we have a perovskite phase here, and the aluminum layer, it oxidizes itself by dragging out oxygen atoms from this thin film, resulting in the oxidation of aluminum into Al2O3. So this process is not very harsh, it's benign. The films retain their crystallinity, and we do not observe any phase separation as a result of this process. So if we look at EELS structure, so if we go from a perovskite film to a square planar nickelate film, looking at the oxygen K-edge, so this pre-peak, so the absence of pre-peak is a sign of the reduction of the transition metal cation, which is what we expect. So nickel goes from 3+ here in green to 1+ in red. We can see similar fine structure changes in the nickel L-edge, where this, the disappearance of this shoulder corresponds to the reduction of nickel going from the perovskite phase to the square planar nickelate phase. So this is from EELS. So now if we look at, so what we do is we do strain analysis using a nanobeam diffraction method. So one thing, main thing to note here is that there is very high compressive strain in the y direction, which is what we expect as the apical oxygens are getting removed. The lattice constant along those direction shrinks to accommodate the strain. And this is the line profile I'm showing here. So we see that as we go from strontium titanate to the square planar nickelate, typically in epitaxial thin films, we'll observe a sharp increase, like a step-like increase at the interface, but we observe a gradual increase in the compressive strain, which plateaus out as we go close to the aluminum oxide. So what is the reason of this kind of strain behavior? So if we go back to the structure, so as we go from the perovskite to the square planar nickelate, what happens is we are removing apical oxygens that would typically be here. So as a result, if we go from perovskite to square planar nickelate, this lattice constant along this direction, it shrinks. So this is what is causing the observation of that compressive strain. So what we see here is that the film is completely reduced close to the aluminum layer, which is now alumina. So, and as we go farther away, there is some retention of the apical oxygen atoms. So close to the interface with the strontium titanate, the film is partially reduced, and about half the thickness of the nickelate film, we yield full reduction, resulting in this NdNiO2 stoichiometry, where we started with NdNiO3. So obviously there are some further process optimization, synthesis optimization that is required to yield the reduced film along the entire thickness. We can also do this kind of analysis using real space atomic resolution imaging as well. So on the so here I'm showing atomic resolution imaging of strontium titanate substrate here and the NdNiO2 film on top. So because since this is a Z contrast image, so we can easily identify and refine the atomic positions for various sublattices. So here I'm using strontium and iodinium. So here we can calculate the lattice constant along the in-plane and out-of-plane direction. So as we can see, the in-plane, the epitaxial lattice constant is fixed to the substrate, which is what we expect, and the lattice constant along 001, which is this direction, along which the oxygens are being removed. We see that it starts to shrink as we move away from the substrate and close to the alumina layer, which is again showing that we can yield full reduction about half the thickness of the film, whereas beyond that it still has some apical oxygens which we are unable to remove using this process. So just for a comparison between atomic resolution imaging and what we can do from 4D STEM, one benefit of 4D STEM is obviously we can map the entire thickness of the film. because for atomic resolution imaging, we require a lot of specific conditions and small noise and changes in the sample tilt, beam tilt, or thickness, or instrument noise renders a contrast like we see on the top, where we cannot clearly identify the atomic columns and we cannot do the strain analysis. But 4D STEM or nano diffraction mode is very robust to this, so we can clearly show the strain behavior along the entire thickness of the film. Moving on next, so now I'll be talking about the effect of high compressive strain on the phase separation and other properties in strontium hafnate. So we use scantinate-based substrate, so terbium scantinate and gadolinium scantinate, and strontium hafnate films are grown under very high compressive strain, greater than 3%. So this is the substrate, and this is the strontium hafnate film. So the reason these things are interesting to study is that because strontium hafnate has a lot of energetically competing phases, and depending on what phase we can obtain, the application changes drastically. We can get films that are suitable for field effect transistors, or we can get films, for example, that are suitable for piezoelectrics. So it's very important to understand how, by controlling the strain, what quality and what kind of phase purity we can obtain in these strontium hafnate films. So again, I'm showing here some 4D STEM data. So this is an ADF image. So here we have strontium hafnate film on gadolinium scantinate substrate, and here I've selected few of the diffraction patterns. So the top is the film and the bottom is the substrate. So one clear on cursor analysis, we can see that we are getting the film is in a different space group symmetry as to the substrate, which is unexpected. So when we look at the in-plane and out-of-plane strain measurements from 4D STEM, what we see along Y is what we expect, because we are applying a very high compressive strain in the in-plane direction. So to minimize the total energy, the film along Y will relax, resulting in a tensile strain here on the Y. But we also see a lot of strain along the X direction, which again is unexpected. So we explore what is the reason for such high strain along the X directions. So we observed that there are some heterogeneities at the interface, and we look at what is the reason for these heterogeneities. First, we observe that there are some formation of a diffusion layer, as we can see here. So the interface is marked with white dashed line. So we can see that there is an intermixed layer that is formed at the interface between the strontium hafnate film and the substrate. This is not ideal because this yields a diffused interface instead of an atomically sharp interface, and results in poor epitaxy. On top of this chemical diffusion, we also see that the resulting behavior in the structure of the film. So here, for example, we see the formation of dislocation as shown marked here, and we also see different crystalline domains corresponding to different structures of the film because the epitaxy is not homogeneous. So the film can now grow into its energetically competing phases. And we also see on the right here that the substrate has a kind of a step edge, so the termination is not consistent, which again results in heterogeneities when we are applying such high compressive strains to grow a strontium hafnate. On top of that, some of the interesting behavior, we see that we do see some signs of polarity as well. So here I'm showing the black boxes here mark that we see the evidence of some polar domains. And we also see some phase separation where we observe multiple phases of strontium hafnate grown under the same condition. So we are in the process of publishing these results, and those results will be later discussed in a manuscript. But what we wanted to show here is that using 4D STEM, we can look at different aspects of structural characterization. So for example, I showed that using 4D STEM, we can look at the extent of reduction in the solid state nickelate thin films. And using 4D-STEM again, we can look at the strain effects in strontium hafnate films under high compressive strain. So ClearView allows us to do these experiments at very high frame rates with high accuracy. And I would like to acknowledge Py4D-STEM, my HyperSpy Python packages that I use to analyze all the data that I showed here. Now I will hand it over to Daniel, who will talk about some of his in-situ TEM measurements.
Thank you, Arash. So good morning, everyone, and thank you for joining us today for this presentation. Today I'm going to talk about the atomic scale tracking of the beam-induced phase transition in MGCR-M04. So I'm going to open up with a very familiar topic, which is going to be the green energy and green resources. So let's take a look at some of the main benefits of the green energy. First things first, sustainability. So the green energy such as wind, solar, and hydro are pretty much important, and they are naturally replenished. It means that we can secure the availability of the energy for the next generation. On the other hand, we have the environmentally friendly behavior and aspects of this green energy, which means that by using this green energies in different systems, in wind and solar farms, we're not going to impact, and we're going to have a minimal impact on the environment. And at last, but not least, unless the fossil fuels, the green energy produces almost no carbons and green gases, which is a crucial important part of our fight with the global warming and the changes on our planet. So being covered with the green energy, we have to take into account another another crucial aspects here, which is if you consider that we are done with producing the green energy in a very efficient way, we have to pay attention to storing this energy in the electric form. So I'm going to talk a bit about the batteries and the battery community. First things first, we know that the lithium as the commercial rechargeable battery, it's well studied and pretty much mature. But also we have other multivalent cations that can be a promising candidate with some advantages to lithium. I'm going to go for the magnesium in this part, which it has a higher energy density due to being a multivalent, enhanced safety, and abundant on this planet, and the lower cost of extraction. So having the magnesium ion batteries, we have to take a look for the structure that can be the host of the magnesium. We can pay attention to a transition metal oxide spinels, which they have some advantages for themselves. That we can name the three-dimensional pathways of cation migration, which comes with a diversity of a favorable inucleation sites, which as we reintroduce the magnesium to our system, there are plenty of these sites that it can sit at. But this material does not come with all advantages, and there are some disadvantages as well here. So if you take a look at this slide, we can see in one study before on the MGCR-M04, after doing the discharging of the battery, there is a formation of the almost 2 nanometer thick layer on the surface of the spinel structure, which you can take a look at it at this figure, which is tagged by E. And this is a charge sample. So in some studies, they showed that this type of creation and the formation of the second phase of the surface of the spinel causes a capacity fading and voltage decay. Also, in another study in our group, we tried to mimic the same spinel to defective rock salt phase transition by exposing the sample to the electron beam. And we found out on this kind of a rock salt phase causes because of the inversion of the magnesium and manganese. And usually this type of defects happens when we reintroduce and remagnetize the sample, and the magnesium going to sit not only at its main site, which is going to be the tetrahedral, it's going to occupy the interstitial octahedral site as well. So let's get into science. In today's talk, I'm gonna point out to 3 different parts of my research, of this research, which is gonna be the in situ TEM, STEM imaging, and EELS analysis. So in this video, we're gonna take a look at the effect of the electron beam on the sample and the dynamic of the creation of this second phase on top of this spinel structure that we have. So if you take a look at it, we see that the layer is just like being created over time after being exposed to the electron beam and the creation of the rock salt or like a cubic structure on top of the surface of the spinel. I'm gonna play it one more time to have a better look at it. And this like formation happens at both sides of this like specific nanocrystal. So if we take a closer look at this like dynamic, we can see that based on this frames which taken from the in situ video, we can see that there is a degradation happening in the first place, and then there's a creation of the second phase on top of the crystal. And if we go for another sample with a higher magnification, we can track this atomic column formation. So from left to right, we can see in a 2 minutes of captured video, and these are the frames of that specific video, we can see the atoms are sitting on top of each other and creating this layer by layer from left to right, indicated by this inset red arrow. And as we can see, over time, this layer grows in this direction, and then the next layer gonna sits on the left side of this layer as well. So in the next part, I bring your attention to the STEM image analysis, which shows the initial and the final states of this E-beam exposure. So in the first place, if you take a look at it here, we do not have any crystal structure, and after being exposed to the electron beam, we can see the creation of the rock salt phase or cubic structure on top of the spinel structure. So we know that this is spinel based on the periodic a change of the intensity and pretty much a familiar diamond shape. But here we can see that there is a change. There is almost a same intensity for each of the atoms in this part, which is a newly formed region on top of the crystal. We took the FFT of this region, and the D-spacing of this FFT perfectly matches the M and O, which is going to be supported by the EELS that we are taking a look at the second phase, which is the manganese oxide. So this is going to be the EELS analysis part, and this HADF image is not corresponding to this EELS, but I put it here to give you a clear view that when I'm talking about the MNO site or talking about the bulk and surface, what I'm talking about. So here we have 4 plots. The red one is the pristine one at the bottom here. Bulk, surface, and MNO-like structures are the regions and sections of the exposed sample. So these 3 are for after being exposed to the electron beam. And if you take a closer look at the oxygen, we can see there are some changes here. For the bulk and the surface, which is going to be this region and this region, which we can see that there is the disappearance of some of the fine details, like this specific peak here for the oxygen. And for the MNO-like structure, we have the absence of the pre-oxygen K edge, which it's supposed to sit at here. Also, I have to point out to this indicator that the black dashed line showing the maxima of the pristine sample and the gray dashed line showing the maxima of the transferred sample. If you take a closer look at the chromium region 5 from 570 eV to 670 eV, we can see that there is no chromium edges L3 and L2 for the newly formed region. So it means that there's no chromium there. And also there's a chemical shift for the L3 of the chromium, which tells us about the change of the valence state of the chromium in the newly formed region and also in the bulk and surface of the exposed sample. And again, if you take a look at another part, another energy range, we can see that there is a significant change in the L3 to L2 ratio of the manganese L edges, and also the disappearance of the manganese on the surface of the crystal. So, which means we again have some changes in this oxidation state, valence state of the manganese in the newly formed region and other regions of the exposed sample here. So getting to the conclusion, I'm gonna talk about that the electron microscopy gives us this luxury to have a better understanding of this dynamic of the transition metal cation migration pathways. And we, in this study, try to demonstrate and mimic a kind of a same phase transition that happens in the electrochemical cycling, which has studied before, and take a closer look at the dynamic of this phase transitions, but not only the initial and the final part of it. And in the future work, by utilizing the power of this high resolution ultra-fast cameras such as ClearView, we can use them in the in-situ electrochemistry to take a look at the atomic scale changes and phase transitions in the actual electrochemistry and electrochemical cycling. Thank you all. I'm gonna hand this presentation to Professor Klee again.
All right, thank you so much. I'm gonna now talk about basically combining these two different approaches that you've seen before, the 4D STEM analysis and the atomic resolution in situ imaging, for a study that we did perform in collaboration with Dr. Chang Lu and his group leader, Paul Alvarsatos. Dr. Chang Lu is a postdoc at the University of Chicago in the Paul Alvarsatos group, and he's been working on in-situ characterization of nanoparticles, self-assembly, and the atomic structural dynamics of materials using advanced electron microscopy such as liquid phase TEM and 4D STEM. So liquid phase microscopy is, as I introduced before, can be done in two different kind of scenarios. One using a silicon nitride based flow cell, where you have the advantage of being able to flow different kind of reagents through the window layer, or you can apply an external field. But of course, due to the thickness of the silicon nitride window layers, there are some limitations to the spatial resolution or the chemical sensitivity that you can achieve during imaging or spectroscopy. For the last 10 years or so, we have been using graphene liquid cells, where you can basically encapsulate a small volume of water between two very, very thin layers of graphene or ultra thin carbon. And this allows you now to do high spatial resolution imaging due to the radiation hardness properties of the graphene. You can also do a continuous EELS acquisition, again with high spatial resolution and high chemical sensitivity. Here are just a couple of examples of the literature over the last 10 years, starting with the crystallization, growth, and etching of particles, the observation of lithium deposition and dissolution in an electrochemical cell that's due to the is done in a silicon nitride cell, as well as the growth and corrosion of particles in a liquid environment, again using an electron beam or using an applied electric field. You can also study the dynamic and nanoscale interaction of particles, of larger scale particles, and under external stimuli. And there are a couple of examples and a couple of references shown here about the various observations here. And finally, you can look at the formation or the properties also of polymeric materials, which are obviously very, very soft materials in a liquid environment using high resolution imaging in the liquid cell of either form. Now, in this case here that I wanted to discuss, we are going to look at the degradation of nanoparticles or the corrosion of nanoparticles in water using the electron beam. And what we do here is we are having the wurtzite indium phosphate in this example here that is being prepared in graphene liquid cells using the processes well described in the literature. And there was a prior study, again by the Alvarsatos group, demonstrating the etching of lead selenide in graphene liquid cells. So we start out with a nanocrystal here, and after a certain total dose, the particles have disintegrated, forming this, or have etched forming this amorphous shell structure and the remaining crystalline core. And they could actually show that this behavior is dose rate dependent, going from 400 to 2000 electrons per angstrom per second. The process, we look at the time scale here, speeds up significantly. Now, what we're doing, or what we have done here, is a comparison between the type of videos and data you can acquire using the RIO camera, and then on the next slide, I'll show you a similar data set using our new ClearView camera. The videos are sped up by a factor of 4, and you can see when I start this video a nanoparticle here in a graphene liquid cell in an aqueous environment at a high dose rate of about 100 electrons per angstrom squared per second. And you can see here that we can get some information about the atomic structure. We can resolve the fringes of the particle, and we clearly can see how the particle dissolves under the continuous electron beam exposure. And you can, this video runs on repeat, so you can see here is the shell, and there are some hints potentially of some shell-like structure forming. Right? But you would like to get some information about the dose rate dependence and also about the etching behavior of those particles as a function of exposed dose rate. And so what we're going to do here is now a switch to the ARM microscopy at UIC and using the ClearView camera. Here's a similar particle now, but in this case, we are using a 5 times smaller dose rate, about 20 electrons per angstrom squared per second. And as I start the video, you can see the particle actually dissolving as well. The video runs on repeat, I hope, and you can then actually see now again that there is some, this is unprocessed data, so you can see some atomic resolution in there, and we can clearly see how the particle etches away as a result of electron beam exposure. Now, after denoising and aligning those particles, we can now actually track very nicely the shape of the particles. And we can clearly see here that we retain atomic resolution even at these very, very low dose rates of our particles, and we get have enough information here to actually see the how the shape and the size of these particle changes during the electron beam exposure and during the in-situ corrosion. Now we can go and look at this in a bit more detail. Here is now a video where we track the particle location, and we also do some more denoising, and you can clearly see here how this particle not only gets corroded, but you actually also see the formation of secondary particles here in adjacent to the particle that's being corroded. And so you see the formation of new crystals. And here are some, on the right-hand side, are about 3 stills taken from the video, the initial particle at the early stages of corrosion, and then about 7 seconds in, where you can see the formation of a halo. And then here, after about 80 seconds and 103 seconds, you can clearly see there are other particles that are forming as a result of the atoms that are being corroded from the original primary particle. Now, this is all done in video mode using the ClearView camera. Now, what we're going to do next is we want to actually see how does the crystal structure of these particles change during the electron beam exposure. And so we are again taking either a very nice high resolution image of these in a liquid environment, or we can combine this now with our 4D STEM capabilities, again in the liquid cells. The 4D STEM now we are taking in similar conditions that Arashdeep introduced earlier in this presentation by initially exposing the particle to a certain dose rate, then switching to 4D STEM mode, taking our 4D STEM data sets, then we are switching back to TEM mode, applying a bit more high dose rate, reasonably high dose rate to advance the corrosion, and then do some more 4D STEM imaging as introduced earlier. Now, here is the, so what you really want to see is the interplay between the crystal structure, the facets, the geometry, as well as the local chemistry, using this combination of high resolution imaging and 4D STEM analysis. So here is what the raw data set looks like. We can see now in 4D STEM mode, as we are scanning across the particle area, you can see there is the majority of the sample is of course the water environment, and so we can see some fluctuation in the diffraction patterns as we approach and scan across the nanoparticle in various stages of corrosion. And so now this allows us to do analysis where we actually are clustering the 4D STEM diffraction patterns and assess the difference between the remaining crystalline core of those nanocrystals, the amorphous surface layer, as well as the secondary phases that will have formed after the advanced stages of the nanocrystalline corrosion. With that, we are at the end of the presentation. I hope we could show you the various different experiments that are now being enabled by the new ClearView camera, ranging from 4D STEM analysis of thin film crystals to in-situ videos of phase transformation at various dose rates, and ultimately the combination of those two, taking videos and 4D STEM data sets under in-situ and in aqueous environments, and really combining this to get a full understanding of the dynamic behavior of nanostructures under various external stimuli. Before we end and open this webinar up to questions, I want to acknowledge various people that have been instrumental in getting this data. Of course, Gatan and Fernando for his continuous support and help with setting up and running these experiments with the ClearView camera. I also want to thank all the my group members, all the members of my group, the nanoscale physics group here at UIC, and Yingji Lu, who has moved on to a permanent position, but she was involved in the early stages of the ClearView camera testing and the liquid cell microscopy work. I also want to thank the folks at Argonne National Lab for providing us with these various samples, the thin film and the battery cathode samples. Feng Yuan Shi is the director of the electron microscopy core here at UIC. Any of the work you have seen is done on the ARM200CF here at UIC. We are a user facility, so you can come and use our instruments here. If you're interested, please reach out to myself or to Feng Yuan to talk about the possibility of using the kind of resources you've seen throughout this talk. I also want to thank the University of Chicago, the Alvesakos Research Group, specifically Chang Lu, for the collaboration that resulted in this fantastic data I showed you at the end with the in-situ corrosion. Ryan Combs and his group at Auburn University for providing the thin film samples, and the Charles Ahn group at Yale University for their nickelate films that you saw in this talk as well. And with that, we have reached the end of the webinar, and we are ready and available for questions. Fernando?
Yeah, thank you, Robert, Daniel, and Arashdeep for this great presentation. It was super interesting to see all the data that you were able to collect with the ClearView camera. As a reminder to everyone watching the webinar, if you have questions, you can submit them through the questions pane here, and we'll get to them either right now or within 7 business days via email. So with that said, we did have a couple of questions come in. The first question, I guess, is for Arashdeep. I know that in the 4D STEM data analysis, you mentioned using Pi4D STEM and HyperSpy. We had a question about what you used to analyze the nano diffraction patterns. So I'm curious if you could answer that, or maybe just give a little more detail for the audience about how you were analyzing the 4D STEM data.
Yeah, so the basic analysis is kind of based on Pi4D STEM and PyMatchen. So we have a very good crystallographic structure information in PyMatchen that is based on materials project. So we can get crystallographic information from there, and then using those simulated structures, we can match the phases that we see in our data, and then use Py4D-STEM to do Bragg vector selection, and then measure, selecting the appropriate peaks in the reciprocal space. We can measure strain measurements using those.
Great, thanks. Another question related to the 4D-STEM data, I guess, is what in general was the total acquisition time for the 4D-STEM data that you were acquiring, especially like the strain mapping data that you showed?
Yeah.
And what was the standard kind of data set sizes that you were working with?
So the total time was around, I would say, 90 seconds, so plus minus 10 seconds. That was for the entire data acquisition. The camera frame rates we were running were close to 1,000 frames per second.
Got it.
Yeah. And the data size kind of varied, but it was around 1.2 to 1.4 gigabytes.
Got it. And what was the size of the spectrum image maps that you were collecting?
The total like memory size?
No, like the image resolution of the mapping area.
Yeah. So so in the diffraction space, we were either switching between 256 by 256 or 128 by 128, and in the real space, it was about 150 pixels by 150 pixels, around that range.
Great, thanks. We had a question come in for Daniel regarding the magnesium battery cathode materials. Could you give some information about how those samples were prepared?
So I'm not quite sure about the preparation of the sample at this point, because I have to contact the guy in the first place. But I think Sol-Gel, as far as I know, and the composition, it's something like Mg Cr 1.5 Mn 0.504.
Okay, great, thanks. Another question I think was regarding the liquid thickness of the liquid cell experiments shown at the end with the indium phosphide quantum dots. Are you able to characterize the thickness of the liquid in the graphene cells?
That's a good question. So we can estimate that the liquid cell thickness is of the order of tens of nanometers. We haven't really done a detailed analysis using EELS, which we can obviously do. But that's sort of like the next step in this series of experiments when we wrap this up for publication. But we are estimates of the order of tens, maybe a maximum of 50 nanometer of liquid surrounding the nanocrystal.
Okay, great. And then, so that's all the questions that we had come in for now that I see. So I think one question I had out of my own interest is, what are the prospects of doing some of these magnesium cathode growth or beam irradiation experiments in combination with the liquid cell environments? Is it possible to do the graphene liquid cell experiments in a more electrolyte type environment for those materials?
I think it's definitely possible or feasible. So there are two different ways that we are approaching this. One would be certainly a graphene liquid cell environment where we are looking at the effects of similar to what we've shown for the corrosion, but in reverse, of electron beam exposure on the transformation of these magnesium cathode particles. A second approach that we are currently working on is using a MEMS-based holder where we actually have a ionic liquid electrolyte, our cathode particles, and then trying to observe the transformation during in-situ electrochemistry experiments. Now, the transformation that we see in those particles when they're used as a battery cathode usually occurs at elevated temperatures. So we have been working on developing a electrochemical holder that can do electrochemistry at temperatures above room temperature, and so we are working right now on combining those two experiments to really do high resolution imaging, potentially 4D STEM, under electrochemical biasing during the reaction to observe this transformation in situ.
Okay, great, thank you. So I think that's what we'll wrap up for today. I want to thank again our speakers, Daniel, Arashdeep, and Robert, for such a great presentation. Thank you all for attending, and we'll see you in the next webinar. Have a nice day.